Hi, this is John Whitaker for the Mathematical Analysis 1 class, and this is our 11th video lecture. And we're in Chapter 2, really getting into the first part of the chapter. The chapter is entitled Basic Topology, and during this lecture we're going to get to some topological features. We'll talk about topological space maybe. But at this point we're still talking about sets, and we're talking about countability and characterizations in terms of accountability or uncountable or finite sets. And so I want to continue that discussion as the book still has information about that. And we start off with the theorem. And the theorem we're going to look at says that if you let A be a countable set and let B sub n be the set of all n tuples A1, A2, up to AN, where AK, one of these coordinates, each one of these coordinates is an element of A, then, or I should say and, the elements involved in this tuple, A1, or the coordinates involved in this tuple, up to AN, need not be distinct. Then, Bn is countable. Now, we're saying this is true for each n that's a natural number, and so a good way of trying to prove this statement is using induction, and that's what we will do. Okay, so the proof is by induction, and we're going to start off with looking at n equal to 1. Then, if you note what B1 is, it's the collection of all, if you will, A1 tuples, such that A1 is an element of A, and this is going to be, if you will, you don't even have to put this tuple about it. You can just say that A, or B1, you don't have to put this parentheses about it. B1 is equal to A. So what that means is, since A is countable, that means B1 is countable. So the statement is true when n is equal to 1. Well, we'll look at for n equal to 2, because it'll be critical for going from the n equal to k to n equal to k plus 1 situation. So B2, B sub 2, will be equal to A1 comma A2, such that A1 and A2 are elements of A. That's what we're looking at. And so for each x A1 in A, the set of the two tuples A1 with anything, where A2 is an element of A, is equivalent to A. So A1 is fixed, and so the second coordinates run through all the elements of A, and so you get the same number of elements in this set for the fixed A1 as what you do in A. And then the way we look at B2, it's equal to the union of all A1s over, or A1s in A, of these types of sets, where A1 comma A2, such that A2 is an element of A. Now, since A, big A, is countable, this is a countable union of countable sets, and so it is countable. I'll write that down. Here's what I just said. I said that V2 is the countable union of countable sets. Okay. And thus is countable. Okay, so we got that V2 is countable. Now, in our induction proof, we're going to assume that for n equal to k, b sub k is countable. And our goal is, what we must do is we must show that b sub k plus 1 is countable. Okay, so we're going to look at b sub k plus 1 in the same way that we looked at b sub 2. We'll say, well, b sub k plus 1, what it's really equal to is the sets of all b, comma, if you will, a, such that b is an element of b sub k. So you think of b being an a1, a2, a3, all the way up to ak, and then to get to something in b sub k plus 1 when we named another coordinate. And a is an element of big A. So, for each b in bk, we fix that, then this b, the set, of all tuples b with a, such that a is an element of a. This is just like what we did for the second case, okay? Is equivalent to A. We did case 1n is equal to 2, just like that. And thus, is countable. And that's for each b in bk. So, b sub k plus 1 equals to the union of all b's element of bk, which we know to be countable, of the sets of b comma a tuples, let's say a is an element of a. So b sub k plus 1 is the countable union of countable sets, and thus is countable. So really, when I said that n equal 2 case was very important, I kind of over-exaggerated that. What it did was showed us the way that we would go ahead and conclude the n equal to k to n equal to k plus 1 case. Okay? All right, but that's the proof. Well, we have a corollary to that. And that corollary is that the set of all rational numbers is countable. And I'm just going to go through the idea of the proof, but essentially what it is that you can let Q, which equals to set of all A, B, such that A, B is an element of the integers with B being different from 0, and then so for each A over B, we can associate to that the tuple AB. Okay? And so this is just a two-tuple, and so provided that Z is countable, the integers are countable. Then Q will be countable. By the previous one. And it can be shown that Z is countable. Okay? So that's what I'm going to say. The way we show that Z is countable, just to comment on this, is to form or to have Z be equal to a sequence, if you will, form a one-to-one correspondence between Z and the set of natural numbers. Did I let you guys think about that? Okay, another theorem that we'll look at is if we let A be the set of all sequences whose elements are the digits zero and 1, the set A is uncountable. And so we want to do the proof of this. So here we'll start off by let A be the set of all sequences whose elements are the digits 0 and 1. So you think of A consisting of all sequences, and each term of the sequence is either 0 or 1. Okay? So that's what we have. Okay, and then we're going to let E be a countable subset of A. So it's just a generic countable subset of A. Well, since E is countable, we can represent it with a sequence. Okay, we can order the elements, if you will. And so we let E consist of the sequences. Okay, so here I'm going to say S1, that's a sequence, okay? Then S2, that's going to be a sequence. S3, forever, okay? Now this is a sequence, so if you will, it has terms, you know, it's S11, S12, S13, and here is S21, S22, S23, okay? So, you know, that's one of the terms I'm ordering. That's the first term of E, and it's a sequence. That's the second term of E, it's a sequence. Since E is countable, I can write down the, I can order the elements of E. Here's the ordering of them, okay? Okay, so now we're going to form, we construct a sequence S. Okay? So this is going to be a sequence S, like this way, as follows. Okay? So if the nth digit of the sequence S of n equals to, or is, 1, then let the nth digit of S be 0. Okay? So look, if this guy is 1, okay, then we let the first guy in S be 0. If this guy is 1, we let the second guy in S be 0. This guy is 1, we let the third guy in S be 0. And so forth, along this diagonal. And if the nth term is equal to 0, then let the nth digit of S be 1. I think that might be overkill, but it's something that can be done. No, we have to have it. That's right. Then what happens is, S is a sequence, okay? And S is going to be in A because it only consists of 0, 1, okay? That's what's happening. But what we have is then S differs from every member of E. In at least one place. So one term of the sequence of the tuples of 0, 1s, if you will. So that means that S is not in E. Not in E. but S is an element of A. So that means that E is a proper subset of A. So everything in E is in A, but A has something not in E. Okay. So, what we've just shown is that every countable subset of A is a proper subset of A. So that means A is uncountable. Because otherwise, if it were countable, it would be, A would be a proper subset of itself, which is impossible. That's the proof. This proof, this statement tells us that the set of real numbers is uncountable as each real number has or can be expressed as a decimal in base 2, okay? And so we think of it at base 2, that means that the entries would be, for a real number, be 0s and 1, and the previous fact says, well, that's uncountable. Okay, so that's a comment. It's a nice thing that this fact gives us. All right, what I want to do next is move on to the basic topology main part of this chapter. And so we're going to start off with a definition. And it says a set X whose elements, we shall call points is said to be a metric space if for any 2 points P and Q of X, our space, there is an associated real number and really it's represented by kind of a function. acting on P and Q. So this real number is d p comma q, d of p comma q, called the distance function. Or metric, such that, so here's what this distance function satisfies. One is that the distance between P and Q is going to be greater than 0 if P is not Q, and the distance between P and Q, the distance between P and P is equal to 0. So if the points aren't the same, they're going to have a positive distance. If the points are the same, their distance is going to be 0. So that has to be satisfied. Oops. 2, the distance between P and Q is equal to the distance between Q and P. And then thirdly, that the distance between P and Q is going to be less than or equal to the distance between P and R plus the distance between R and Q. And that's a statement that's true for every R that's element of X. So this is the qualifications that need to be satisfied by this distance or metric function, by this metric, and a space that has set that has this type of function on it is called a metric space. Okay? Okay, we're going to look at an example. Okay, and so if we let x be equal to rk and define d of p, the distance between p and q, where p and q are in rk, as the norm between p minus q where this is the norm on r. Then x coupled with this metric is a metric space. In terms of notation, I'm using double bars for norm. Our book uses single bars for the norm in chapter 1. I'm accustomed to using these double bars, but every once in a while I might use single bars. I've got to put any parentheses there. Okay. We proved that this p minus q satisfies the conditions to be a metric by our work in chapter 1. Okay, so I'd like for you to refer back to that if you need to. But I will say something about how we show the second part that needs to be satisfied for a metric is satisfied by this. And so, in particular, the distance between P and Q equals the distance between Q and P. This was the second thing. As the distance between P and Q, as we're defining it in RK, is going to be equal to this norm of P minus Q, which can be thought of as the scalar minus 1 times Q minus P. And what we proved is that is equal to the absolute value minus 1 times the norm of Q minus P. And absolute value minus 1, of course, is 1. So this is Q minus P, which is the distance between Q and P. Okay, so mainly what we're going to be doing the rest of the time is definitions. And here's some terminology we need to know about. So definitions. First thing I want to say is the book says by the segment AB, we mean the set of all real numbers x, so real numbers x, such that a is less than x is less than b. It's just this open interval. But they're going to call it a segment. So that's my first definition. Two, second definition, by the interval a to b, we mean the set of all real numbers x such that a is less than or equal to x is less than or equal to b. It's kind of our usual definition, this interval. Then we have something called half intervals. Call them half open intervals. And so what we have here are two types. We have A to B with brackets about A, parentheses about B. Of course, what we mean here is this x is in R such that A is less than or equal to x is less than b. And then the second type is A to B, parentheses about A, close brackets about b, and that's the set of all x's in R, set of all real numbers, such that A is less than x, which is less than or equal to b. Okay. And then I have a couple more definitions. So fourth definition, if AI is less and bi for all I equal 1, 2, up to k, then the set of all x's equal to x1, x2, up to xk in Rk that satisfies AI is less than or equal to xi, which is less than or equal to bi. And that's true for I being sandwiched between 1 and k, is called a K-cell. It's called a K-cell. Okay, so as an example, if we look at A equaling to the set of x in R2, such that 0 is less than or equal to x of 1 is less than or equal to 1, and, I'll write down here, 0 is less than x of 2, which is less than or equal to 3. Okay. This is a 2-cell. So what it looks like graphically, so it's in R2, I can graph it in R2. The first coordinate, which we'll think of as the x-axis, has to be between 0 and 1, here. And the second coordinate, which I'll think of as the y-coordinate, has to be between 0 and 3. Maybe I'll make one a little smaller. And let's say that's 3. And we're looking at this rectangle where we include the borders. Okay, so that's A. Okay. Next thing I want to find is if x is an element of Rk and R is greater than 0, the open, and I'm also going to find closed, ball. B, centered at x and having radius r. Okay. So here, maybe I should call this B sub r of x. So this is B sub r of x is equal to, it's the set of all y, an element of Rk, such that the norm between x minus y is less than r. That's what it is. So it's the distance, it's the points in Rk whose distance from x is less than r. That's the open set. Or, here we denote the closed set by B sub r. I guess I shouldn't have put a notation here. So let's take that away. B sub r of x, centered at x. We put this bar over to represent the closed one. So this is the open one. It's a set of all y's, element of Rk, such that the distance between x and y is less than or equal to r. Okay? That's the closed, that's the open. Open, this is closed. Closed ball. All right, now we've still got a series of definitions upcoming. Those right here had to do, that I just listed, had to do with kind of intervals in some sense in R or RK. Or balls. But now we're going to go, to get away from RK or R, we're going to go to just a generic metric space and talk about some definitions there that will be vital to us. Okay. Here's some definitions. So it says let X be a metric space. Okay. And then one thing here that we want to make a comment about is all points and sets mentioned in the definitions below are understood to be, so if they're points, they're elements of X and subsets of X. Okay, so we've got a series of definitions here. The first of which is a neighborhood. So it's an extension of something we just saw. So a neighborhood of some point P in X is a set n sub R of P consisting of all points Q such that, all points Q, such that the distance between P and Q is less than R. Okay, and R is called the radius. Of n sub R P of this neighborhood. Okay. And so that is analogous to the definition we just gave a few seconds ago about the open ball in RK. I'm going to do an example in R. Okay, so as an example, this definition I'm going to give. If we said, if we consider X to be equal to R1, so that's my metric space, the absolute values here is going to be the metric so these are real numbers with respect to the difference of them inside absolute values. Then, if you were to look at the neighborhood with radius 1/2 about 2, what you're looking for is all the real numbers whose distance from 2 is less than 1/2. So this is this segment, as the book would say, from 3/2, 1.5, up to 2.5, so that's 5/2. So for now. Okay. Another definition is a point P is the limit point of the set, sometimes it's called accumulation point, of the set E. So it's a limit point relative to the set E. If every neighborhood, we usually abbreviate neighborhood, okay? It's a long word. Sometimes we just write down in neighborhood like this, NBHD. If every neighborhood of P contains a point Q that's different from P, such that Q is in E. And so as an example of this, if you look at the set 1 over n, this is the sequence, and there are a set of real numbers, then 0 is a limit point. So this is my set E. Oops. But I want you to tell you that you can note that 0 is not in E. So a limit point doesn't have to be in the set. It can be in the set, but it doesn't have to be. Okay, the next definition we're going to look at is if P is element of E and P is not a limit point when we mean of E, then P is called an isolation point, or isolated point of E. And so if we think of the real numbers, if we look at E, this is an example. If we look at E equaling to something like -1 to 3, that segment union with the number 5, then 5 is in E, but it's not a limit point. So it's an isolation point, an isolated point. Okay. Another definition is that E is closed, so a subset of X is closed, if every limit point of E is a point or an element of E. So to be closed, you have to contain all your limit points. Okay? And so as examples, the set 1, 3 in this way is closed in R with our metric that we have defined. And then also J equal to the set of 1, 2, 3 is closed. Okay? And the reason it's closed is that it doesn't have any limit points. So it contains all the limit points that it has. Okay, another definition, E, is a point P is an interior point of a set, interior point of E, if there exists a neighborhood of P, let's call it N sub P of R, so there's some positive radius here, such that N sub P of R is a subset of E. an example of this. Let's example this, and we'll do one more definition, and then that'll be enough, and we'll start next lecture with some more definitions. So, example. If you look at E equaling to minus 1 to 3, then 0 is an interior point. And the way we think of this, look, here's minus 1, here's 3 on the number line. This is our set. 0 is sitting right here. And what I do is I just put an open neighborhood. I put a neighborhood about 0. I find one such that this neighborhood is totally contained in minus 1 to 3. And a neighborhood you could pick is 0, the neighborhood about 0 whose radius is 1/2. Now, in the same example, minus 1 is not an interior point, and neither is 3. And the reason is that every neighborhood about minus 1 will not be contained. So none of the neighborhoods about minus 1 will not be contained solely in minus 1 and 3. They have some guys, some part of the neighborhood will be in this set, E, but not all of it. And the same thing goes for 3. Okay. Here, this last definition that we'll do today, this was out, says E is open if every point of E is an interior point of E. So, as examples, if you look at E equaling to minus 1 to 3 that's open, that is open. And that's what we have. And the way that you can come up with the neighborhood is that if P is an element of E, so I'll just write it down to let you think about it, then we define R, the distance that we want to talk about, that establishes what the neighborhood is. If you take the minimum between the numbers 3 minus P and P plus 1, that will be your, can be your radius. Okay, ladies and gentlemen, that's enough for this video lecture. Thank you very much.